2.3 Continuity. A function is continuous if you can trace its graph without lifting your pencil from the paper. So there are no holes or asymptotes or breaks of any kind in the graph. This is a very informal definition of continuity. You can't give this kind of response on the AP test. Okay, continuity over an open interval means that the function is continuous at each point in the open interval. And here is a definition you want to get used to. A function f is continuous at x equals c if all of the following conditions are true. 1. F of c is defined. 2. The limit of f of x as x approaches c exists. And 3. The limit of f of x as x approaches c is equal to f of c. Okay? And this c value, x equals c, that c value is that possible discontinuity. Okay, a possible value in the function where we can, where it can be discontinuous. Violations to the conditions. Case 1, f of c is undefined. Okay, so this is an example where we have a function with an open hole, rational functions. I'll explain what can cancel denominator means. Okay, but when we have an open hole, or rational functions where we cannot cancel the denominator, again I'll explain that later, but where we have a vertical asymptote. Case 2, f of c is defined, but the limit of f of x as x approaches c does not exist. Okay, so for example, a piecewise function where we have this break going on. And case 3, f of c is defined, the limit of f of x as x approaches c exists, but the limit of f of x as x approaches c does not equal f of c. So that's kind of where we have a function with an open hole at an x value. However, there is a dot on that same x value, okay? But we still have an open hole on the actual function. So that dot is kind of somewhere outside of the function. Piecewise defined function. One piece is a rational function where you can cancel the denominator. I'll explain all of this later. Okay, now discontinuities. Points where a function is not continuous. Okay, so there is one case that we call removable discontinuity. A discontinuity where the limit of f of x as x approaches c exists, and the limit, and f of c is undefined, or the limit of f of x as x approaches c does not equal f of c. Okay, so let's look at an example of a removable discontinuity. So here we have x squared minus 4 over x minus 2. So we know that we have a possible discontinuity, or we know that this is not continuous at x equals 2. Okay, you know that when x equals 2, the function, we get the denominator of 0. Okay, so let's see. When we do f of 2, so when we do f of 2, we plug in 2, we get undefined. Okay, let's not get the 0 over 0 indeterminate form. Let's not get that confused with the limit process. I'm not talking about the limit as x approaches 2 right now. So I'm not talking about the limit as x approaches 2 yet. I'm talking about f of 2 undefined. However, the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, this is indeterminate form. This is where we want to do some kind of simplification, some kind of algebra, which is factoring x squared minus 4 Now, remember when I said I would talk to you guys about canceling the denominator? This is what I mean by canceling the denominator. So see how having 2 was a problem because we would get the denominator, or x equals 2 would be a problem because the denominator would be 0. Now we got rid of that. We canceled out that denominator. So we get, so the limit of x plus 2 as x approaches 2 is now 2 plus 2, which is 4. This is a removable discontinuity. Because the limit of the function as x approaches 2 exists, but f of 2 is undefined. Okay? Oh. Okay, so let's look at another example. Oops. Oh, there it is. So now let's look at a piecewise function. Okay? So this time, notice that there's something going on at x equals 1. So in that last example, our x equals c. C was 2, that possible discontinuity going on at 2. Now this possible c value, that possible discontinuity is at 1. Okay? So here we know that, okay, f of 1, not f of 2. Now, f of 1 is when x equals 1. So for f of 1, we are looking at 2. So f of 1 is equal to 2 based on this piecewise function. Now, before we can answer the limit as x approaches 1, we got to ask ourselves what's the limit as x approaches 1 from the left, and the limit as x approaches 1 from the left. That's the case when x is less than 1. So we're going to be looking at this function x. Okay, now that we've identified what function we're looking at, we are not going to put that superscript of 1. We do our direct substitution. This is just 1. The limit as x approaches 1 from the positive side of the function will very similar to x approaching 1 from the negative side. Now we're looking at values when x is greater than 1, so we're going to look at 2x minus 1. That's the limit of 2x minus 1 as x approaches 1. No more superscript. That's 2 times 1 minus 1. So it's 2 minus 1, which is also 1. So because they came out equal, we can say that the limit of f of x as x approaches 1 exists, and it is equal to 1. However, notice that f of 1 came out to 2. So here what we have is, again, a removable discontinuity. Because the limit of f of x as x approaches 1 does not equal f of 1. Oh, before we do that, add this to your notes. Now there's a case called non-removable discontinuity at x equals c. That's discontinuity where the limit of f of x as x approaches c does not exist. And that's this case here. F of x equals 1 over x plus 3. We know that this x cannot be negative 3. We have a vertical asymptote there. Also notice that unlike the first example, we can't cancel the denominator. There's nothing we can do. And the graph of that actually looks like this. You don't need to draw the graph. Don't worry about drawing the graph. Just know that there is our asymptote, vertical asymptote. Notice that it goes to negative infinity as x approaches 3 from the negative side, and it goes to positive infinity as x approaches, and I'm sorry, that's negative 3, as x approaches negative 3 from the positive side. Okay. So that last one, this one right here, is an example of non-removable. So this has a non-removable. Discontinuity at x equals negative 3, since the limit of 1 over x plus 3 as x approaches negative 3 does not exist. Okay, so I showed you a few examples of removable discontinuities, and here's one of non-removable. So 2 of removable, 1 that's non-removable. Okay, try doing this one, and then we'll discuss. I wanted to get to this one, but I only have about 1 minute and 10 seconds. So try doing this one, and we can discuss it in class tomorrow. Okay, so the possible c value would be 2. Okay, the possible discontinuity, the possible break would be at 2. Okay? And then let's end it with this little side note. A polynomial function is continuous everywhere. Okay? The trig functions f of x equals sine x, f of x equals cosine x are continuous everywhere. That's going to help you guys a lot. And that is it for today.